Hello everyone, welcome to my new tutorial on binary numbers and logic levels. This will be an introduction to digital electronics. First, we might want to know what a bit number is and how we create binary numbers. Recall from our previous lectures that transistors are composed of three parts. We have a base, a collector, and an emitter. When a transistor behaves as a switch, it operates between the saturation and cutoff regions. When the current at the base is greater than zero and it is high enough to saturate the transistor, it conducts in the saturation region. The collector current will be at a maximal level, which is called IC-SAT, and the voltage between the collector and the emitter is zero, because now the switch is closed. This is what we call a logic state of zero or false, because we have zero poles between the collector and the emitter. But when the base current is zero, its operation is within the cutoff region and the transistor is no longer conducting. The switch is open and the voltage between the collector and the emitter is V plus, or the supply voltage. This is what we call the logic state of 1 or true, because we have the voltage between the collector and the emitter. We can say that computers operate by using millions of transistors working together, each of which is either on or off. The state of each bit or transistor is called a bit, the smallest unit of data that can be stored by a computer. Remember, a byte consists of 8 bits. Okay? Digital electronics operate with only two voltage levels, logic 1 and logic 0. Okay, so you can say that we have voltage and no voltage. Okay. It is because of this reason that almost every digital electronic system uses the binary number system. Okay, and hey guys, the English alphabet is in binary code, which is called ASCII code. Okay, something that I want to mention is that the binary system is also a position value system, where each bit, in this case, let's say we have 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay, we have a 1 byte. Okay, each bit has its own value or weight expressed as a power of 2. We have the first place, second place, third place, and so on. So how do we obtain these values? Well, let me show you how. Consider now the following binary number consisting of 8 bits again. The bit at the leftmost position, let's say this one, is called the most significant bit, and the bit at the rightmost position, which is this one, is called the least significant bit. Okay? So how to convert from binary to decimal? Well, first of all, you need to identify the position values and of course their corresponding weights of each bit working from right to left. Okay, let's say so this one, and this will be your least significant bit, its position is number 0, so you need to multiply the value of the corresponding bit, which is 1 times 2, which is the base number system, to the 0 power, and that will be equal to 1. Again, position number 1, you have 0, so 0 times 2 to the first will be equals to 0, and so on. Notice that if you compute the following operations, let's say 2 to the 0 power, that will be equal to 1, 2 to the first will be equal to 2, 2 to the second will be equal to 4, and so on. Notice that the exponent describes the bit position, the base is number 2, and the result is the corresponding decimal weight. At the end, we will have the following series, number series expressed as a power of 2. This one, 1, 2, 4, 8, 16, 32, 64, and 128. So, how to obtain the decimal equivalent number? Well, if a 1 appears, okay, if a 1 appears such, this one, we have 4 ones, I think, okay? So, if a 1 appears in a digit position, add this to the remaining weights to obtain the decimal equivalent, okay? So, you have 32 plus 16 plus 4 plus 1, that will be equals to 53. So, that will be your decimal value for this binary number, okay? So, now consider the following binary number. notice that there are 5 bits, okay, 5 bits to the left of the binary point, which is this one, and there are 4 bits to the right to the binary point, okay? These 5 bits, okay, represent the integer part of the number, and the remaining 4 bits, let's say they're located to the right of the binary point, represent the fractional part of the binary number. So places to the left of the binary point are positive powers of 2, whereas the places to the right of the binary point are negative powers of 2. So consider now that we have only to the left of the binary point we have 1, 2, 3 number ones. So we need to add, again, 1 times 2 to the 4 plus 1 times 2 to the third, 1 plus 1 times 2 to the first, okay? And again, we need to add the remaining weights, okay? But now the positions are negative, okay? At the end, you have the following series numbers, and you need to add the remaining weights. So, if, for instance, we have 16, which is this number, 8, which is this one, number 2, which is this one, 1/2, 1/4, 1/16, and this will be your decimal value for the corresponding binary number, which is this one. Okay? So, what happens when you press a key? Well, the keyboard sends an electrical signal called the scan code to a computer, saying that the button was pressed. The keyboard controller interprets the scan code and determines that the letter pressed has an A or B or whatever using ASCII codes. ASCII stands for American Standard Code for Information Interchange. So, for instance, if you press key, which is letter A, let's say, so letter A, capital A, is encoded with 65, so its corresponding binary number will be equals to 010001. Okay? So how to convert from decimal to binary? Well, it's a short division by 2 with reminders. Okay? So there's a repeated procedure. For instance, consider now the following number, which is 245 in decimal. So divide the number by 2, and you will obtain 122. So write out the remaining number, which is 1, and continue dividing by 2 again, and you will obtain, let's say, 61, and write out again the remainder number. Okay, continue until the resulting value, let's say this one, 1 divided by 2 is equal to 0, and write out the last remaining number. Okay, the most significant bit is the remainder value located at the bottom. Okay, and the least significant bit is the remainder value located at the top. So the corresponding binary equivalent number of 245 will be equal to this one. Okay, guys? Now, your turn. Here's your class activity. Convert the following numbers to the indicated bases. Okay, you need to convert from binary to decimal. Be careful with these two examples, capital M and letter M. You need to locate, let's say, you need to find out an ASCII table, convert it to decimal, and then to binary. Okay, upload your homework via Blackboard during this week. Thank you.